This is slide number 41 and I am your presenter Asloob Mudassar. The topic is field calculation in free space. Before we start the topic, let's understand the diagram. These are two planes parallel to each other. This is xy plane and this is again xy plane. Both are parallel to each other, separated by a distance z0, and both are piercing the z-axis perpendicularly. The field on the first plane at z is equal to 0 is labeled as a capital U at x comma y comma 0, and the field at a distance, the same field when propagate and when reach at a distance z0, on that plane the field will be regarded as capital U at x comma y comma z0. So if we assume that this field which is at z is equal to 0 plane, that is u of x comma y comma 0 is known, we want to find the field at a distance z0 which will be labeled as u of x comma y comma z0. So you see that this is the problem that we are going to address. And okay, let's now read some statements. An optical field has to pass through space between any two optical components in an optical system, which is regarded as the propagation of a field through free space. So you see that here this field capital U at z is equal to 0 will propagate a distance z0 and will reach at another parallel plane. So you see that this space between them is the free space. Now U at x comma y comma z is the known field, is the field known at the xy plane located at z is equal to 0. The field is propagating to the right along the z axis, and this field, which is u of x comma y comma z0, is the field to be determined at the xy plane located at a distance z is equal to z0. The problem is to express u at the position x comma y comma z0 in terms of the field at z is equal to 0, which is u of x comma y comma 0. U may be considered to consist of superposition of plane waves of different amplitudes, phases and different propagation directions. So you see that here we are assuming that this field, which is our initial field at z is equal to 0 plane, which is u at x comma y comma 0, is the field which it may be a complex field, and we may consider this to be a consisting of the superposition of plane waves of different amplitudes, phases and different propagation directions. The Fourier spectrum of such a wave on any plane perpendicular to z-axis will break the complex wave into its component plane waves having different amplitudes, phases and propagation direction. The component waves form part of the angular spectrum, which is A at fx comma fy is equal comma 0 of the complex field, this one. So you see that if we want to understand the angular spectrum of that field, we have to consider the Fourier transform of that one. So recognize the integral on the right hand side in equation 75. This is nothing but the Fourier transform integral, and the Fourier transform of the quantity is u of x comma y comma 0. So we are taking the Fourier transform of this quantity. On the left hand side we have a at fx comma fy comma 0. So you see that this A, which we are calling at the moment as the angular spectrum at z is equal to 0 plane, is actually the spectrum, is actually the Fourier spectrum of this field, which is u of x comma y comma 0. So this angular spectrum you must keep in mind that we are calling it as an angular spectrum, but in principle this is the Fourier spectrum. And you know that this term you can recognize e to the power minus iota 2 pi within the bracket. We have we have fx into x plus fy into y are the elementary waves propagating in the directions determined by. So you see that the directions in which these elementary waves will travel are given by, because these depends upon fx and fy, and fx is equal to cos alpha over lambda and fy is equal to cos beta over lambda. For each wave cos alpha and cos beta, that is alpha and beta, will be different, and of course fx and fy will be different. So substituting these different values over here, we can calculate the angular spectrum at a different Fourier, at a different spectral frequency, or at a different Fourier variables. and fx and fy, you know, that are the Fourier variables. So you see that these are the elementary waves propagating in the direction determined by this one with weighting factors u at x comma y comma 0 as amplitudes. So in this integral, you know that this u can be regarded as the weighting factor or the amplitudes of these waves. Alpha beta are the angles the propagation vector of each wave makes with the x-axis and y-axis. We have assumed that u at x comma y comma 0 is known. So you see that in the problem this field at z is equal to 0 is known. So that's why the angular spectrum is also known through this equation 75. So on the right hand side, since u of x at u at x comma y comma z is equal to 0 is known. So the left hand side, the angular spectrum A at fx comma fy and comma 0 is also known. So equation 75 can be inverted. That is u of x comma y comma 0 can be expressed in terms of the angular spectrum using inverse Fourier transform definition, which is given in 76. So you see that we have seen before the equations in 75 was the Fourier transform equation, and the equation number 76 is the inverse Fourier transform of equation. And you know that in the inverse Fourier transform we have substituted the angular spectrum. All the variables in the inverse Fourier transform are the fx and fy variables. And so you know that on the left hand side we have the space variables x comma y, and here z is equal to 0. Assume that an angular spectrum A at fx comma fy comma z is equal to 0 or z naught is associated with the field u at x comma y comma z naught. Then following the equation 76, a similar relationship is given below. So you see that we have written this equation in which angular spectrum A at z is equal to 0 position is known. But you know that we have also written equation number 77. Look at this equation. This is the same as this is the same in comparison. This is similar to the equation number 76. But here the only difference is that we are using the angular spectrum, which is located at a distance z is equal to z naught. The rest of the things are the same, and on the left hand side we have the field which is u of x comma y comma z naught. So you know that in this equation 77, angular spectrum A at the position z naught is unknown, and that's why the field on the left hand side which is u of x comma y comma z naught is also unknown. So if we can make a connection with the angular spectrum at z naught to the angular spectrum at z is equal to 0, we can determine the unknown field in equation number 77, that is u of x comma y comma z naught. So let's see how we shall do, we shall carry on the calculations. U of x comma y comma z naught is unknown, and so does a of fx comma fy comma z naught. To find this, that is to find u of x comma y comma z naught, we have to determine a at fx comma fy comma z naught first. U of x comma y comma z naught being an optical disturbance must satisfy the Helmholtz wave equation. So let's substitute this one in the Helmholtz equation as in equation number 78. So let's expand this one in two steps. So del operating on u and also k square operating on u and is equal to 0. And you know that del in the Cartesian coordinate system is del square is equal to curly square over curly x square plus curly square over curly y square plus curly square over curly z square. Using u at x comma y comma z naught from equation 77 into 78 we have. So you see that we have u over here from equation number 77. We are using u of x comma y comma z naught from equation number 77, and we are substituting that one in equation number 78 to compute all the three components of the del square, that is curly square over curly x square will be operated on u, and similarly curly square over curly y square will operate on capital U, and similarly curly square over curly z square will operate on capital U, and the u will be nothing but the u will be provided by the equation number 77. So the first derivative that we are going to compute over here is curly square over curly x square. and you know that we can send this operator inside the integral on in the first row, because curly square over curly x square is a linear operator. It will not operate on the angular spectrum, because the angular spectrum has no variable which contains x. So only the exponential factor contains x variable. So curly square over curly x will operate on the exponential part of this problem. So you know that we shall first the first differential will give you the second step, and the second differential will give you the third step of the integral, as in equation number 79. So that's in the third step we have actually evaluated the double derivative of the field on the left hand side, which is u of x comma y comma z naught. Similarly, we can evaluate the double derivative curly square over curly y square operating on this field, and we can write the integral number in equation 80 in equation 80 similar to the equation 79. You can see that only the only difference is that the variable fx over here, for example, will be replaced by fy over here, and the rest of the things are the same. But you know that when we carry out the calculation with curly square over curly z square, it will be different, because this part will not operate on the exponential part, because the exponential part has no x z dependence variable. It will only operate the angular spectrum, because the angular spectrum A at fx comma fy comma z has a z dependence. So after we take the double derivative of this quantity, we shall have to evaluate this at z is equal to z naught, because we have to determine our field which is u of x comma y comma y at a distance z is equal to z naught. So first of all we shall keep z over here. We shall carry out the second derivative with respect to z. Then we shall put the then we shall replace z is equal to z naught in equation number 81. Now you see that the k square u, if you multiply the k square u, you will get the same integral from here we started, and only the k square will multiply. So we have evaluated, you saw that in the equation number 9 we have calculated the derivative with respect to x. In equation number 80 we have calculated the derivative with respect to double derivative with respect to y, and in equation number 81 we have calculated the double derivative with respect to z, and in equation number 84 we have just multiplied k square on both sides. So you know that then we have all the fields calculated over here, and now we are going to substitute all these calculations in equation number 78. The three derivatives that we have calculated will be substituted in the place of del square u, and we have k square u calculated also. So substituting these in equation number 78. So after substituting that in equation number 78, we have obtained equation number 83. The common factors in that equation will be cancelled out, and also the integral will also be cancelled out. The common part of the integrals will also be cancelled out, and we are left with this one. So you see that in this equation we have replaced the partial derivative is the exact derivative. So we have d square of d square over dz square operating on the angular spectrum A of fx comma fy comma z, and then we have some terms that is square of 2 pi over lambda square, and then we have in the curly bracket 1 minus lambda fx whole square minus lambda fy whole square, and then we have again a as our angular spectrum at the end, that is A of fx comma fy comma z, and the curly bracket will be evaluated at z is equal to z naught, and then we have that one is equal to 0. So this is equation number 83. This is, if you look at this equation 83, this is the differential equation. This is a second order linear homogeneous differential equation in A solution of this following a solution of the following form can satisfy the differential equation. So you see that in equation number 84 we are suggesting a solution of this differential equation, and of course this satisfies the differential equation if you try this one. So this is the solution of the differential equation yet that we are suggesting. And then you know that we have in the solution we have substituted z is equal to z naught. So this is a particular solution located giving us the solution at a distance z is equal to z naught. 84 gives you the general solution for any value of z. But if you put z is equal to z naught, you will get the equation number 85. This is the angular spectrum evaluated at a distance z is equal to z naught. So actually we have a angular spectrum which has propagated distance z is equal to z naught. The initial angular spectrum, you know that this is connecting the initial in equation number 85 we are connecting the angular spectrum at a distance z naught equal to the connecting to the angular spectrum at z is equal to 0, and then some phase factor is being multiplied over there, which is e to the power iota 2 pi over lambda, and in the square root we have 1 minus lambda fx whole square minus 1 lambda fy whole square, and the z naught is also multiplying to the exponent part. All the terms on the right hand side of equation 85 are known for a given value of fx, fy and z naught. So if you substitute fx, fy and z naught in equation number 5 on the right hand side, then you know that the angular spectrum on the left hand side will completely known. Using this value from equation number 85 into equation number 77, we get this. And what was equation number 77? Equation number 77 was containing this angular spectrum and of course this exponential factor, which was the exponential factor that appear in the definition of the inverse Fourier transform. And you know that we have just replaced the angular spectrum a of fx, fy, z naught by this quantity, which is a of fx, fy, 0 multiplied by e to the power iota 2 pi over lambda into 1 minus square root of 1 minus lambda fx whole square minus lambda fy whole square, the square root of these quantities, and multiplied by the z naught value. So you know that this equation on the left hand side we have the field which we wanted to determine, and on the right hand side we have all the parameters which are known. That is the angular spectrum. Initial angular spectrum is also known. The exponent factor, if we put the value of fx, fy and z naught, this is also known. The rest of the quantity is also known. So the field at the distance z naught is also known. So you know that it means that the field which was u of x, y, 0 at the plane z is equal to 0. Now we are now able to find the field at the position z is equal to z naught in terms of the angular spectrum of the field which was known. For an arbitrary distance z, the equation 86 takes the following form. So you see that rather than making a particular substitution, that is z is equal to z naught, we are replacing z naught by our distance z, so that we can have a more generalized solution. That is, for any value of z, the field is given by u, or is given by equation number 86, which is u of x, y, z, and on the right hand side we have the integral which I have already explained. This derivation assumed, you know that in the derivation we assumed infinitely large planes, that is these planes with which we started, these two planes were infinitely large. There were no limitation on the size of these planes. So you see that these fields, the fields at the z is equal to 0 plane and the field at z is equal to z naught plane, these fields are defined on an infinite plane. So the derivation that we have reached contains the planes which is of infinite extent. For example, this one. But you know that in real practice the planes are not infinite. So we have to limit the size of the planes. So we limit the size of the plane with some circular region, and for that one we can use the circ function. To limit the size of the input plane into the circular region of radius r0 centered at the origin of the coordinate axis, we can introduce a circ function, or the circular function abbreviated as a circ function, defined below. So circ in polar coordinates r over r0 is equal to circ in Cartesian coordinates square root of x square plus y square over r0 is equal to 1. This first definition is in terms of the polar coordinates, which is equal to 1 for when the radius r over r0 is less than 1 and 0 otherwise. So in this region, that is in the polar coordinates that we have defined over here, so this definition of the circ function we have given in terms of the polar coordinates over here. So you see that it means that when the radius of the disk is less than equal to r naught, then we have a clear aperture in which the amplitude is 1, and otherwise we have the amplitude is equal to 0. It means that outside that circular disk of radius r naught, the region is opaque and no light can pass through that region, no field can pass through region. So the field only will pass through a circular region of radius r less than equal to r naught. Assuming a circular aperture at the input plane, the expression of A at fx, fy, 0 in equation number 75 takes the following form. So what we are going to do is that we are going to multiply a circ function over here. So you see that we have multiplied a circ function over here, but not in this equation, but in equation number 75. So let me show you the equation number 75 over here. So this is the equation 75. So you see that this was the input field and the circ function should appear in the input field over here. So let's see that how the equation 75 was modified when we are limiting the aperture of our field. So you see that this is the same field and we have just multiplied the circ function in terms of the Cartesian coordinates, and then of course we have the same definition of the angular spectrum. So you see that here angular spectrum is the angular spectrum of this field, and but this field, because this is the Fourier transform definition of this field of the angular spectrum, but here we have multiplied the circ function in this field because we have the variables of integration is x and y. A circ function in the spectral domain to limit the bandwidth, or equivalently the angular spectrum to lie within a circ of a radius 1 over lambda, can be defined as. So you see that here we are giving the circ definition. Again we have used circ of rho over rho, and rho over rho, what is rho over rho naught? Rho over rho naught is actually the parameters of the polar coordinate system in Fourier domain. So rho and rho naught are the, rho naught is the variable of the polar coordinate system in Fourier domain, and rho naught is the radius. And we are using another definition of circ in polar coordinate system in Cartesian coordinate system. We are using the Fourier frequencies in the Cartesian system as fx square plus fy square root of these two. So 1 over lambda is actually the size of this circle, or the radius of this circle. So you see that the circle, the first definition we have given is equal to 1 when rho over rho naught is less than equal to 1 and 0 otherwise. So first definition is for the if we are using the polar coordinate system in the Fourier domain. If you use the polar coordinate system in the Fourier domain, then the circ will be defined by rho over rho naught, and x in the explicit form the definition will be equal to this one. So if you are using now the Cartesian definition but of the circ function in the Fourier domain, then you have a circ of square root of fx square plus fy square root of then over 1 over lambda is equal to 1 or 0, and fx square plus fy square root of that one is less than equal to 1 over lambda and 0 otherwise. So this is the equation number 89, in which we have given two equivalent definitions. One is in the polar coordinate system, the other in Cartesian coordinate systems, both in Fourier domain variables. The expression of u of x, y, z in equation 86 when we limit the size of the aperture is given by. So this is that definition. You can see that now we have the field on the left hand side which we wanted to determine, and on the right hand side we have the double integral over the variables dfx and dfy, and we have the initial angular spectrum multiplied by the circ function in the Fourier domain now, which is fx square plus fy square, and the square root of these two quantities divided by 1 over lambda. 1 over lambda, you know that it defines the bandwidth of the circ function in the Cartesian coordinates in the Fourier domain, and you know that this is the free space propagation factor that we have evaluated over here, and then you know that this equation is multiplied by this exponential factor, which is due to the definition of the inverse Fourier transform. Okay, the physical meaning associated with limiting the size of the input angular spectrum is equivalent to convolve the input field over the infinite plane with appropriate Bessel function, which can be found by taking the Bessel Fourier transform of the circ function in equation number 90, which is given. So you see that in here what you have the angular spectrum multiplied by the circ function. Both the circ function and the angular spectrum are using the Fourier variables, but you know that when we define them in the space domain, actually then the inverse Fourier of this quantity, which is the field at u of x comma y comma 0, and the inverse Fourier transform of the circ function, which is also the circ function but in the space domain coordinate, but then these two variables will convolve with each other. Here they are multiplying in the Fourier domain, but in the space domain these two quantities will convolve with each other, which we see over here. So let's take the Bessel Fourier transform, because we know that when we talking about the polar coordinates, we invoke the variable capital B, which stands for the Bessel Fourier transform of the circ function rho over rho naught. And you see that here we have also used B over with the Cartesian coordinates. You could also use tau over here. So you know that the Fourier transform in Cartesian coordinates for the circ function is J1, Bessel function of kind 1, order 1, and within the parenthesis we have 2 pi rho naught r or divided by rho naught r. And you know that we have expanded this J1, that is we have expressed this one in the Cartesian coordinates in the bottom, where we have J1 within the parenthesis we have 2 pi into 1 over lambda, and we have square root of x square plus y square, and divided by 1 over lambda into the square root of x square plus y square. And this is equation number 91. The presence of the circ function with the angular spectrum in equation number 90 means that the input field this is modified to a new field this, which is found. So what we say that this angular spectrum and the circ function, these two together give you a new angular spectrum, a limited angular spectrum, and of course the limited field, the new field, which we call as u prime over here. So u prime at coordinates x comma y comma 0 is actually a new field, you know that. And here we have taken the inverse Fourier transform of multiplying these two variables, that is the angular spectrum and the circ function from the above equation, and we are taking the inverse Fourier transform, because the inverse Fourier transform of these two will give you a new field. If you remove the circ function from here, then the inverse Fourier transform of this angular spectrum will give you the field u of x comma y comma 0, the original field. But you know that since we have multiplied a circ function over here, and then we have taking the inverse and then we are taking the inverse Fourier transform of the product of these two quantities, that is the initial angular spectrum and the circ function, of course. Then we have a new field which we are calling as or labeling as u prime at the initial condition, at the initial coordinates x comma y comma 0. And if we evaluate the inverse Fourier transform, then you know that the inverse Fourier transform of first quantity convolved with the inverse Fourier transform of the second quantity. And here the inverse Fourier transform of the first quantity, the angular spectrum is the original field which is known to us, that is u of x comma y comma 0 is known. And after the convolution we have the inverse Fourier transform, the circ function, which is the circ of fx square root of fx square plus fy square over 1 over lambda. So you see that these two convolve together. It means that when we are using the circ function, so you see that this field which over here on the left hand side, u of x comma y comma 0, this field was defined on the infinite plane, and when it convolves with the Bessel function of the Fourier transform, then you know that this field which is u prime of x comma y comma 0, this is not defined on the infinite plane, but it is defined in a circular region of a radius that we have also mentioned previously, radius r less than equal to r naught. So this is what we have explained, you know that that is the field on the left hand side, which is u prime of x comma y comma 0 is the field which is defined in the circular region, and the field on the right hand side, which is u of x comma y comma 0, is the field defined on the infinite plane convolved with this Fourier transform of the circle function. So this is, I think that this is now well explained. Let's go ahead. So this A angular spectrum at fx comma fy comma 0 is the angular spectrum of the field is the angular spectrum associated with the field u of x comma y comma 0, and this that is A of x comma y comma fy comma 0 multiplied by the circ of square root of fx square plus fy square divided by 1 over lambda. Actually this is the angular spectrum associated with this field, which is u prime of x comma y comma 0. Thus the convolution of a field with appropriate Bessel function results in limiting the angular spectrum associated with the field. Let's reproduce u of x comma y comma z from equation 77 for comparison with the same quantity from equation number 90. So we have the quantity in equation number 90, that is this one, and we have another expression for this one which we have reached earlier, and this is what we are reproducing that result over here. For example, over here in equation number 93, if we compare this equation with that equation that I have shown you earlier, then you know that the comparison will reveal that this angular spectrum is equal to A of A at fx comma fy comma z is equal to A at fx comma fy comma z is equal to 0 multiplied by the circ function, that is the circ of square root of fx square plus fy square divided by 1 over lambda multiplied by this free space propagation factor, which is e to the power iota 2 pi over lambda, and the square root of 1 minus lambda fx whole square minus lambda fy whole square, and multiplied by the z, which is not in the square root but as a part of the exponent. So you know that these two can be regarded as simply that we can write the initial angular spectrum as such, and the other quantities, that is a circ function and the exponential function, that is the free space propagation factor, we can together write them as k. So k of fx comma fy comma z. So you know that now the relation due to the last step in equation number 45, in equation number 44, in equation number 94 is quite simplified. That is the angular spectrum at the position z is equal to the angular spectrum at the position z is equal to 0 multiplied by free space propagation factor, which is k at fx comma fy comma z. So z means that z is the distance after which the angular spectrum, initial angular spectrum, will be modified to give you on the left hand side the angular spectrum at a distance z. So what is the meaning of k of fx comma fy comma z? Is known as the transfer function of the wave propagation phenomenon. It gives information about the transfer or propagation of a Fourier spectrum over a plane with the change of propagation distance z. So look at that, this equation is in the Fourier variables. So Fourier spectrum, this is the Fourier spectrum. On the left hand side we also have the Fourier spectrum. So now we are going to write down the transfer function in equation number 95, which you can see that very easily, that this transfer function, that is k is equal to e to the power iota 2 pi over lambda and the square root of 1 minus lambda fx square minus lambda fy square, and z outside this square root and multiplied by z. Z is the part of the exponent, and this will hold for fx square plus fy square the square root of that one when that is 1, that is less than or equal to 1 over lambda, otherwise the k is equal to 0. Now we are going to discuss some definitions of the transfer function. We have the transfer function in equation number 95. So let's discuss some characteristics of this transfer function. The bandwidth control. The bandwidth will be controlled by 1 over lambda. It is non-zero in the region. The square root of fx square plus fy square is less than or equal to 1 over lambda. So 1 over lambda is actually controls the bandwidth of this transfer function. or if so this the maximum value is provided by 1 over lambda. So if you want to remain within this limit, then the bandwidth will be set up using fx comma fy. Linearity. Wave propagation phenomenon is linear as it depends on the unit power of the variable z. You can see that in the exponential part of that one we have single power of z, which means that the wave propagation phenomenon is linear. Dispersive spatial filter. Dispersion would be observable with non-monochromatic waves in which a range of lambda is possible. So dispersion would be observable with the non-monochromatic waves. So you see that if many wavelengths are present, then you know that in this expression which we have only single wavelength, but many wavelengths if present, then for each wavelength, then of course for each wavelength the k value will be different. So we shall have the dispersion spatial filter in that case. Phase dispersion. It is due to the exponential factor. For fixed lambda, it is introduced with the propagation distance z. For fixed z, phase dispersion increases as we move away from fx is equal to 0, f is equal to 0 on the fixed plane. So you see that our phase dispersion will come out due to this factor, that is the square root of this one and iota 2 pi over lambda, then the square root term, and then of course z. So the phase dispersion will arise from what? It will arise from lambda, it will arise from the value of z, it will arise due to the values of fx and fy deviating from their values in the center, which is fx is equal to 0 and fy is equal to 0. So on the final plane, on the Fourier plane, where in the center we have fx is equal to 0, fy is equal to 0. If you move away on that plane, away from the center in the Fourier plane, then of course the dispersion will appear. But if you have some fixed values, for example, at some point if you have fixed the values of fx and fy, then you know that the phase dispersion will appear if you allow z to change. So you see that these are the factors that I have covered in the phase dispersion. Then unit magnitude. Within the bandwidth defined by this one, that is the square root of fx square plus fy square is less than or equal to 1 over lambda, the modulus value, the mod value or the magnitude value of the capital K defined at fx, fy, z is equal to 1. This what you can easily see, because this depends upon the complex value, and so if you take the amplitude of that value or the absolute value of that one, then you know that you are left with only 1, because the absolute value will disappear. And so the angular spectrum suffers only through the phase shifts with no change in magnitudes. So magnitude, you know, that remains the same throughout the region of the bandwidth. Space invariance. The propagation phenomenon based on capital K at fx, fy, z is space invariant, because the inverse Fourier transform relationship based on equation number 94 is a convolution relationship which is given next. So you see that we can write down, for example, inverse Fourier transform of the angular spectrum at the value of z is equal to the inverse Fourier transform of the angular spectrum multiplied by k. So if you take the inverse Fourier transform of each of these quantities, then you know that the Fourier transform of the angular spectrum convolved with, so there should be a convolution sign over here, which I have forgotten in the second step, and the inverse Fourier transform of that one, and that convolution sign is I have written in the third step. So remember that in the second step you should also have a convolution sign between the two Fourier inverse transform quantities. So you see that on the inverse Fourier transform on the left hand side of the angular spectrum will give you the final field, which will be u at x, y, z. So on the left hand side you have the field which is u of x, y, z, and on the right hand side you have the initial field which is u of x, y, 0 convolved with kappa. So what is kappa? Kappa of x, y, z. So kappa is actually the appeared due to the inverse Fourier transform of capital K, which is the transfer function. So we can regard this kappa as the point spread function. kappa of x comma y comma z may be regarded as the point spread function of the wave propagation phenomena. So kappa is the inverse Fourier transform of capital K and may be regarded as the point spread function of the inverse Fourier transform of the propagation phenomena. Now the summary of the calculation of unknown fields. If you have a field which is unknown, how the summary of the calculation of unknown field u of x comma y comma z, how will you calculate that one? You see that we have listed all the above steps in greater detail. Now we are precisely listing down the steps that would be required in order to evaluate or in order to calculate this field, that is the field at a distance z. So the first step is that compute the angular spectrum this, which is a of fx comma fy comma 0 from the known field at u, that is u of x comma y comma 0. So this field was known. From this known field, calculate the angular spectrum a of fx comma fy comma z is equal to 0 using equation number 75. The second step is that set the bandwidth using square root of fx square plus fy square less than equal to 1 over lambda, and compute transfer function capital K at fx fy comma z using equation number 95 for a given z. Compute the angular spectrum A at the position z, that is a of fx comma fy comma z, from the product of the initial angular spectrum and the transfer function of the free space propagation phenomena using equation number 94. Compute the inverse Fourier transform of both sides of these quantities to find this one, and the Fourier transform is just we have mentioned over here in equation 96. So you see that these are the steps that I have mentioned over here that you can use in order to calculate the field u at x comma y comma 0, that is the u at the position z. Now let's discuss some more details about this transfer function. Let's give now more details about the transfer function. Introducing fx is equal to cos alpha over lambda, fy is equal to cos beta over lambda, and keeping the fact that cos square alpha plus cos square beta plus cos square gamma is equal to 1, we can write the above transfer function in the following form. That is the capital K of fx comma fy comma z is equal to e to the power iota 2 pi over lambda, and within the square root, and within the square root we have a 1 minus cos square alpha minus cos square beta, and outside this square root we have z multiplying to the power to the exponent. And you know that we can also express the quantities in the square root in terms of the cos square gamma, and we can write it as e to the power iota 2 pi over lambda multiplied by cos gamma multiplied by z value. And you know that this will hold when cos square alpha plus cos square beta, the square root of that quantity is less than or equal to 1. Otherwise this quantity, that is the transfer function, is 0 if you go beyond this region. That is, if you go beyond the region of cos square alpha plus cos square beta, the square root of that one is less than or equal to 1. If you go beyond that region, then of course you will have 0 over there. For a moment, assume that cos alpha, cos beta, cos gamma are not direction cosines, and that they can make values, that they can take values greater than unity, such that mu is equal to cos square alpha plus cos square beta minus 1. The square root of this quantity is greater than 0. So you see that here we are assuming that these are not directions cosines. Then what will happen? Then you know that mu quantity is introduced by this factor, and then mu will be a positive quantity. So the transfer function in that case becomes equal to this one. So we have a capital K at fx comma fy comma z is equal to e to the power minus iota 2 pi over lambda into mu into z. And then you know that of course we have the limit that cos square alpha plus cos square beta, the square root of that one is greater than 1. When it is less than 1, we have the cos alpha and cos beta as the direction cosines, but if it is greater than 1, then these are not the directions cosines but some other quantity. So you see that this quantity is greater than equal to 1, and we have also proved previously that mu is also greater than 0. So when mu is greater than 0, and then you know that if lambda is fixed, then if you increase the value of z, what will happen? This will decay very immediately because it is an exponentially decaying factor. The angular spectrum relationship given in equation number 94 then takes the following form. So we have the angular spectrum on the left hand side at a position z is equal to the angular spectrum at a position z is equal to 0 multiplied by the transfer function, and now we are using the transfer function values, which is e to the power minus 2 pi over lambda into mu into z in the last step. And of course we have also mentioned that the square root of cos square alpha plus cos square beta is greater than 1. It means that these are not the direction cosines. So you see that the initial on the right hand side you can see that the angular spectrum A will decay exponentially with the distance z. That is, angular spectrum attenuates exponentially with z in the region this. Waves corresponding to that part of the angular spectrum are regarded as evanescent waves. These waves diminish after a distance of a few optical wavelengths and are usually not captured by any optical imaging system. These waves do not carry any energy away and are associated with the sub-wavelength details of the object within the aperture. Some modern microscopy based imaging systems exploit these waves for sub-wavelength detail. So if you want to capture the sub-wavelength detail, you have to capture these waves which are decaying very immediately, which we regarded as evanescent waves. Before they decay, you need to capture them if you want to acquire the sub-wavelength detail of the object. If a very thin and very fine grating elements are placed just after the illuminating apertures, evanescent waves may couple with such grating elements, resulting into generation of traveling waves which can propagate longer distance and can enter into a precision imaging device. So you see that in this paragraph we have mentioned a technique that how you can place a grating elements just before the object which generates the evanescent waves, so that you can couple with the grating elements those evanescent waves, and then those evanescent waves can travel longer distance and can reach the precision imaging systems where they will enter or capture by the system. And then of course we can obtain high resolution imaging, that is the sub-wavelength imaging, using this technique. Now more detail about the input field. We only know that the input field is this u of x comma y comma 0 on the xy plane at z is equal to 0. Assume that a unit amplitude normally incident plane wave 1 into e to the power iota phi. 1 is the unit amplitude of the normally incident plane, and e to the power iota phi is the phase value of that plane wave, illuminates a thin planar object or aperture with amplitude transmittance equal to Ta of x comma y comma 0 located at the z is equal to 0 plane. So we have a place an object whose transmission amplitude transmittance is denoted by Ta at position x comma y comma 0, and this object is illuminated by a unit amplitude plane wave that we have mentioned over here, amplitude 1, and the phase factor is e to the power iota 5. So then the field just before that aperture is equal to 1 into e to the power iota 5, just before that object, and then the field just after that aperture or that object will be equal to the field multiplied by the amplitude transmittance of the object, which is e to the power iota 5 multiplying by Ta, which is at x comma y comma 0. But you know that in the first step we have written this field as u of x comma y comma 0 as 1 multiplied by the amplitude transmittance Ta of x comma y comma 0. Why we have multiplied? We have multiplied because we can disregard the constant phase factor of the plane wave, because a constant phase factor, if a phase is constant on a plane, then you know that this will not change the physics of the problem, and then we can disregard such a constant. So in the last step we have disregarded of that constant. So this is the technique that we have mentioned, how to write over u of x comma y comma 0 when we are normally illuminating an object with a unit amplitude incident plane wave. Now suppose that our plane wave is not a plane wave but is a complex wave, not incident normally. So let's regard that complex wave as u subscripted to c at x comma y comma 0. Then you know that we can write field just before the aperture is u c of x comma y comma 0, and the field just after the aperture is u c multiplying by the amplitude transmittance of the object, which is a ta. So our field in this case will be equal to u of x comma y comma 0 is equal to uc at x comma y comma 0 multiplied by ta at x comma y comma 0. So uc of x comma y comma 0 may be an inclined plane wave or a spherically diverging plane wave or any other wave. If uc of x comma y comma 0 has a regular pattern, then such an illumination is called structured illumination. So here this is the end of slide number 41.